Welcome to this Building Infiltration webinar hosted by the Green Building Council of Australia. My name is Robert Milagre. I'm the Director for Sustainability Services and Reporting here at the GBCA. My role here is essentially around the technical robustness of the rating system, as well as the certification process. We're joined today by a couple of guest speakers. We have Chris Nunn with us. Chris is the Head of Sustainability Property at AMP Capital. AMP Capital has a property portfolio valued at approximately $20 billion, mainly in Australia and New Zealand. And that includes shopping centers, offices, and industrial parks. Chris's experience spans over 15 years. His experience is very broad and varied, including environmental law. He was part of the Environmental Defender's Office in Sydney. He has also worked in the UK, in London, as an Associate Director for Sustainability at Atkins. Chris has watched the development and progress of building infiltration in the UK, so he has a particular interest around that topic for Australia. He also worked in consulting here in Australia with Norman Disney & Young, and he was also a former sustainability director at JLL. He joined AMP Capital back in September 2015. Thank you for being here with us, Chris. We're also joined by Sean Maxwell. Sean is the president of the Air, Infiltration and Ventilation Association of Australia, which is a group pushing for better building performance through improved air tightness of buildings and ductwork. Sean's worked for building science consulting firms in the United States for 10 years. His main focus has been a multi-unit residential research during his time in New York. He has published work for the Department of Energy's Building America program on the links between building air tightness and ventilation performance. Thank you for joining us, Sean. As you can see, we have a pretty strong group of people here with you today to talk about this very interesting topic. Now, just before we get on to the topic itself, just a couple of housekeeping notes. You should be able to see the control panel there in front of you at the moment. You should choose the mic and speakers setting to VoIP. We're not using a telephone today, so if you cannot hear me, you should try and switch to mic and speakers. But I guess if you can't hear me, you won't be able to listen to this instruction. So you can always type in a note in the enter a question box. This presentation will be recorded today, so you will be receiving a copy of the presentation with sound later in the week. A couple of notes on how to ask questions. You'll see in that box there that you have room to type questions. We would request that you type in your questions throughout the presentation. There will be time for answering questions at the end. You don't need to wait until you get to the end of the presentation to ask your questions. Actually, it's actually better for us if you type your questions throughout. And then at the end, we'll take some time to answer some of your questions. We'll also aim to answer all of the questions we don't get to today on our website later in the week. So let's get started. So I'll start with a couple of notes on building ceiling air tightness in Green Star, and then Chris Nunn will take on from there, followed by Sean Maxwell. So at the moment, building ceiling is tackled in Green Star in two particular areas. In Green Star Design and As-Built, within the greenhouse gas emissions credit, there are a couple of prescriptive pathways, meaning when people are not doing an energy model, so when people are using I guess, deemed to satisfy methodology within the building code to try and comply with the criteria within Green Star. When they're using that pathway, there's one point available for non-residential projects. If a project team simply goes through an air leakage test. So the idea here is that we're trying to introduce this concept to the Australian market. So there's a couple of standards there that we quote. So if a project team goes through and carries out the test and reports back on the results, they'll be rewarded with 1 point. The same is true for residential buildings that use the NETHA's pathway. Same deal there, slightly different standard. It's based on a dwelling instead of non-dwelling. There are some, we provide some guidance within the submission guidelines for Green Star Design and as-built on pages 144 and 145. We talk about a couple of standards and guidelines that we currently refer to, and then we provide some good practice and best practice figures just for information, and both Chris and Sean will talk about these later on. However, within Green Star Design and as-built, you're not required to achieve any particular good practice or best practice outcome. You're simply required to carry out the test and report the results back to the GBCA. However, there's some other criteria within the innovation category. There's an innovation challenge in which project teams can achieve up to 2 points by doing a couple of things. Testing out how tight their facade is, but also achieving some best practice air tightness results. The reason why this is in innovation, it's because the Australian market is not quite there just yet. So this is one of the ones that we're trying to push project teams even further. Again, we provide a best practice outcome target for project teams to reach towards. And this is where, for the innovation challenge, for the second point, you would have to actually meet those targets to achieve an outcome. So that's just a very brief introduction where we have started tackling building ceiling and air tightness in Green Star, since it's such a new concept for the Australian market. Okay, so that was just my initial spiel there, and Chris Nunn will carry on with his part of the information.
All right, thanks everyone. Thanks for that introduction. I'll jump right into the content here. So air tightness in Australia is a great unknown. There is not a lot of data about the infiltration rates and the air tightness and air permeability of commercial buildings in Australia. But what we do know is that our buildings are probably quite leaky. And a study by Luther, who's a professor down at Deakin University in 2007, estimated that our buildings are between 2 and 4 times leakier than those in Europe and North America. So there's unrealised potential to improve energy efficiency and comfort through air tightness rectification works. And in my view, it's a bit of a forgotten piece of the energy efficiency puzzle. We largely focus on services upgrades, which is probably the logical, cost-effective place to start. But as commercial buildings move up the NABERS performance improvement scale toward the top end, we should really be thinking more about fabric. And in fact, in the UK, it's the fabric first approach rather than, and then services and then renewables that really dictates the path to a low carbon building. So there's some examples here from studies around the world saying what kind of proportion of energy or heat loss is associated with infiltration in commercial buildings. Carbon Trust puts it at 35%, Emmerich and Orm even higher figures. It's going to be less in mild climates. Obviously, it's not going to be up there at 35% as it would be in a colder climate. However, we think it's probably in the order of 5 to 15%, so maybe 10%. Still significant saving across a commercial building when you think about the next slide being this nested pie charts of the split in energy of a commercial building between the base building energy consumption and the tenancy, and the area highlighted shows that which might be attributable in terms of the services energy to the building fabric. So obviously if we have a better building fabric, better insulation, better glazing, better sealing, We're going to use less fan power. Our chiller's going to have to work less hard. Our pump's going to have to work less hard. Our cooling tower's not rejecting as much heat, and we're not doing as much heating in winter with our boilers. So we could nibble away at various parts of the energy consumption of the services, and we might conservatively say that we could achieve a 7.5% total building energy saving by improving the air tightness. Other potential benefits beyond those operating cost savings are capital savings associated with the reduced size of mechanical plant and equipment. If you've got a tighter building, you need less energy to cool it, and you need smaller pieces of plant and equipment to do that. You might improve the control and therefore your ability to maintain temperatures inside the building. You might have better control over condensation risk, interstitial in particular, improved comfort conditions for the people inside, improved air quality potentially is particularly important in places like China now. Indoor air quality is a huge issue there. Noise, you'll have better acoustics, and the quality of construction will generally be improved by the better attention to detailing through the design process. I won't dwell on this international standards piece, but suffice to say, for your reference, there are a range of international standards around both the process for testing air tightness and the standards that you should try and achieve. The main way we achieve air tightness testing is through blower door testing. You pressurize the building and then you look at it using thermographic imaging and use smoke pens to determine where the leakage pathways are. Once you've done that, you've pressurized the buildings and you've identified some of the air leakage sites, you can take remedial steps to minimize leakage and improve air tightness, and then you'd probably retest the building to characterize the improvement of the whole building air tightness. So that's simplistically what air tightness testing involves. And I'll just touch on minimum standards around the world. There's no requirement in the building code of Australia to minimize the actual performance of, or improve the performance, infiltration performance, or minimize the infiltration. We have a section, part J3, which relates to air infiltration and sealing, but it really just says, please put in place some rudimentary seals, but unfortunately there's no numerical testing requirement, and there's no performance outcome specified in the standard, and there's no checking. So it's really a bit like if we were saying, you should have insulation please, but we're not going to tell you what R value it is, and we're not going to check if you actually put the insulation in. So you can kind of imagine what the result is. If you did that with insulation, no one would put insulation in because no one's checking. That's what we're doing with air tightness currently in the building code. There's no real requirement to do it. In contrast, my UK experience was that from 2002 onwards, air tightness criteria were gradually introduced into the equivalent of our Section J, Part L of the UK Building Code. In 2002, they introduced for buildings over 1,000 square metres. In 2006, buildings over 500 metres squared. And then finally in 2010, all buildings over 1,000 metres squared had to test and achieve an air permeability less than 10 metres cubed per hour per metre squared of facade area at 50 pascals of pressure. And that 10 is a pretty reasonable target to achieve, particularly in a commercial building. And this is just a slide around international standards. You can see that in Sweden, the minimum standard is 2.2, Denmark, Norway, 2.5, Germany, Finland, 4, Italy and the UK, 10. So you can see that in the colder countries, they've got tighter infiltration requirements, and that's sensible because they've got more heat loss through the fabric in colder climates. This slide shows a comparison of our air tightness performance and minimum standards between the UK, Germany and Australia. In Australia, we really don't know what the building infiltration statistics are for commercial buildings, so I've put that at the far left end of the scale there. As you can see from the previous slide and what I've discussed, the UK code is 10 metres cubed per metre squared per hour at 50 pascals, and in Germany the code is 4. And Passive House, arguably the world's best practice standard on air tightness, infiltration, thermal bridging and fabric performance, the standard is down at 1. So that gives you a sense of the scale, and I put the smiley face traffic light indicators to show what standards say is good. Excellent is at 2 in a commercial building, good is at 5, anything worse than 10 is probably not very good. So you can see that if we're up around, I don't know, 15, 20, then we're really not in line with good practice internationally. And I've done that same thing for fabric U values and glazing, both in terms of the glazing U value and the solar heat gain coefficient, but I won't dwell on those two things because the rest of the fabric is not really the focus of today. So what is good performance? As I mentioned in the previous slide, there are some international standards. One of them is the Chartered Institute of Building Services Engineers Technical Manual 23, Testing Buildings for Air Leakage, and it says good practice is 3.5 in an office and best practice is 2. There's another one, the UK Air Tightness Testing and Measurement Association, which says similar, good practice is 2, okay practice is 5 for a commercial office, and you can see in this graph here we've compared the two. So consensus that best practice is below 2, which is what's been picked up in the Green Star credit for the 2 points once you test a building. A little bit of variance in terms of what good practice is, but somewhere between 3.5 and 5, and probably the minimum standard being 10. So there's only one study in Australia that's looked at commercial building air tightness that I'm aware of, and that was by Egan, published in ERA in 2012. And that tested 6 commercial office buildings in Canberra. And what you can see here is the results, the infiltration results, ranging from 6 up to 17. They're the blue bars. Now you can see I've overlaid the UK minimum standard at 10. 3 out of those buildings would have failed the minimum standard of the building code in the UK, introduced in 2010. And none of them would have achieved what is considered normal by ATMA, the UK authority, and none of them would have achieved that good practice level of 2. So that's interesting, and it sort of validates what Luther said about probably our buildings are pretty leaky. Certainly in Canberra, these 6, they're pretty leaky. Now this next slide is actually commercial building air tightness testing results provided by Mike Rogers from Air Barrier Technologies, which is one of the company that does blower door testing. And what you can see here is that there is a range of performance. At the good end, you've got some down at that 2 level on the left-hand side, an archive and an office that are actually the only ones hitting what's considered to be good. And that's actually a really great achievement, that there are some in that group that are hitting that. One just under 5, so that's still quite good. A police station, which was I think about 7. So they're all in a pretty good situation, but they were in fact designed to achieve an average air tightness criteria of 4. So they were designed to be tight, and they can achieve it. So the good news from this graph is that it is possible to achieve air tightness in Australia if you try. But most people don't try, and most people don't measure. So the result we get is that the average across this sample group is that the air tightness is 26. So that's not very good. So most of them are pretty bad. Most of them are failing the building code in the UK and are actually really, really leaky by international standards. I think the good news there is with some simple rectification works, you can improve an average of 35 meters cubed per meter squared per hour at 50 pascals down to 11, which is actually not bad. You can make them 70% tighter with some simple rectification works. So Egan estimated that you could achieve between 5 and 15% whole building energy savings from halving air leakage. So if we improve our air tightness by 70%, then we can expect to be in this range of, so maybe middle of that range, 7 to 10% of energy savings. So the range of savings that we could expect in Australia is not like the international range. You can see in this slide there's a summary of some of the international studies that have shown between 2 and 45% whole building energy savings from improved air tightness. In Australia, we expect that to be smaller, but we think there's still a significant saving to be had in Australia. Another area of saving is ductwork air tightness. The building code actually does now call up the Australian standard for duct leakage. For those ducts over 3,000 litres a second, they should be tested, and the leakage should not be 5%. Well, actually, typically, ducts can be leaking 20% of the air that's put through them, and you can imagine how much energy is being wasted, both in terms of the direct fan power, pushing the air through those leaks, rather than to the space where it was intended to be delivered, and also by the chillers in cooling that air down that gets wasted by being vented in the plant room or some other duct run in a non-conditioned space. So we have a problem both with the fabric on the outside of the building and with the ducts that are providing our mechanically conditioned air into our spaces in conditioned space. So infiltration and air tightness is a really big issue and a really big opportunity for improvement. There is technology that can improve existing building ductwork air tightness, and that's technology called AeroSeal, and they pump a vaporized aerosol gel into the sealed up ductwork that then congeals as it finds eddy currents around the leaks and seals up those gaps, and you can achieve significant improvements in ductwork air tightness through that kind of rectification work. So there are simple things you can do to improve air tightness. So in conclusion, there is room to improve in Australia. We think we could get Australian buildings probably 70% more airtight through simple remedial steps, and that could deliver significant savings of in the order of 10% across a whole building. we should be moving to a fabric-first approach in terms of our approach to energy efficiency in buildings, and for air tightness testing criteria to be set in the brief for new buildings when we build them, and indeed for major building rectification works. There's some interesting work going on in this space. Myself, along with Craig McLaughlin of the University of Wollongong at the Sustainable Buildings Research Centre, applied for a City of Sydney research grant, and that was awarded to us. And so Craig's leading some research that will look at the methods of air tightness testing that we should use in our mild climate in Sydney, and what the potential energy saving benefits of doing that might be. And we're also hosting a group air tightness catch-up call, so if anyone has a particular interest in air tightness and would like to participate in a more general discussion about progress toward incorporating air tightness testing in the building code or in improving air tightness testing generally, then please get in touch with me. I think my contact details will be provided, and you can join those calls. So thank you very much.
Hello, everyone. Can you hear me? I hope so. All right. So my name is Sean Maxwell. I'm an American who came to Australia last year in February, and wanted to get work doing what I was doing back in New York City, which was testing buildings, and found out there's just not that much work going on here. And so I became a member of the Air Infiltration and Ventilation Association of Australia. It's a mouthful. And our goals are to really standardize the way people are doing blower door testing here in Australia, and basically become a quality control body for ourselves to ensure that we're all doing the same test and doing it well and reporting it correctly, so that the data can actually be used. We are also trying to put some proposals for change into the construction code to improve the miserable air tightness standards that are in there currently. So, blower door testing. Basically, I'd like to start with a question: why wouldn't you do a blower door test on your building? And some of the typical answers, maybe you can pick one of these. You don't see any real benefit to doing a blower door test, or you don't know how much it costs. It's an unknown. It seems complicated, and you don't really understand it, see what it's worth. Or I've actually heard this when I've gone to do presentations to some pretty big companies. They said, well, you know, actually, if we do a blower door test on one building, then we actually know how leaky it is, and if that's written down on paper, now it'll be compared to other buildings, and it's almost better not to know, which I don't think is really the right approach. It would seem like you would want to know how you're doing so that you can tell how you're going to improve. So Chris talked about this quite a lot, so I won't dwell on it. Problems caused by infiltration, they're pretty obvious. One of them that I'd also like to highlight is poor smoke and fire containment when you don't have proper air sealing between compartments in a building. But I always get this response when I say you should seal your building as tight as possible. Some people say, yeah, oh, no, absolutely right. You should seal your building as tight as possible, except you should leave some leakage, right? And I say, no. Is some leakage good for a boat? Is some leakage good for ductwork? Any of you mechanical engineers in the audience? Wouldn't you rather have your ductwork be completely airtight? Is some leakage good for a fire separation when you have a smoke refuge in your building? Is some leakage good for a laboratory where you have to get dressed up? No, leakage is not good. How do you basically, the next slide will show this other simple adage people always use. Buildings have to breathe, and that makes my skin crawl when I hear it. It's not true. Buildings don't have to breathe. Buildings have to dry. People have to breathe. So buildings they'll get wet. They start out wet. They're built with wet construction materials. It rains during construction. Buildings get wet but the function of a building is to stay dry so that it doesn't rot, and then to keep the people inside dry. So people are what have to breathe, and ventilation is actually a very, very small requirement. So I just for illustration purposes, a 50 square meter apartment contains 120,000 liters of air, and the Australian standard for ventilation calls for 10 liters per second per person. That's every second. That's 0.008% of the apartment volume. It's an incredibly small amount of air that you actually need to meet indoor air quality. So if you should strike that buildings have to breathe saying from your mind and replace it with these very useful sayings here. Build tight and ventilate right. If that's the only one you remember, then that's good. Okay. First, the next thing people say is, well, what about condensation? What if you get condensation in your building because you seal it up too tight? Listen, getting water in your building is bad, but you don't answer that by making it as leaky as possible to dilute the moisture. You keep the moisture out to begin with by using a good building envelope, and then you can gain control of the air in the building that will allow you to control the moisture in the building. So just for example, 2 sheets of plasterboard, if you have one of them with a small hole in it, and then considering equal environmental conditions on the inside and equal environmental conditions on the outside, you'll get 9 times more air through that little hole than you would through the entire board, the entire sheet of plasterboard. So much more air, much more moisture is transported by air leakage than through moisture diffusion. So there's definitely a premium for building a green building, and I guess I won't dwell on this, but except to say that if you get a higher neighbors rating, you can command higher premiums in rent or in building value. And this graph, when I saw it, made my jaw drop. This is a graph from a GBCA report, Achieving the Green Dream, Predicted versus Actual Performance. And this is a chart that shows whether buildings that went through the Green Star program achieved what they said they were going to. And for the most part, they did, but there were a couple of them on the right here where they really missed the mark. And you can ask yourself, why did that happen? I know that some of this, in fact, probably a great deal of it has to do with when you build a new building, you need to commission it correctly so that all the systems are operating correctly. I totally agree with that. And it's also possible that the people doing the energy model didn't model it exactly how the building was built in the end. But there's also probably a possibility that some of the construction wasn't up to what was assumed. The installation, air sealing, things like that. So blower door testing, or air tightness testing, what is it? There's a few different ways you can test a building. One is with a blower door, which I'll spend most of the time talking about. One is with tracer gas testing, which is basically you put one machine in the bottom of the building and it lets off gas, and then you put other little machines throughout the building and test how long it takes that gas to make it to the other locations. And another method is using the building's own HVAC system as the blower door apparatus. So you use the air handler to pressurize the building and then measure the air going into that to find out how much, how airtight is this building. I could talk about that a little bit more. I personally don't think it's the way to go for Australia because it turns out to be pretty complicated. I've done many hot wire and pitot traverses of ductwork trying to get airflow measurements and then trying to coordinate something like that with measuring the pressure differences on a big building. I think it's beyond the expertise of most testing firms here in Australia, and blower door testing is a lot more straightforward. So there's so many standards. Chris outlined even more than there are here, but the couple that I want to point to are, the first one is, did you know that Australia has a blower door testing standard? It's AS 9972. It was published late last year, and pretty much all of these standards use the same ideas, the same procedures. So once you do a blower door test, you can report leakage by lots of different metrics. One that's common for homes is air changes per hour at 50 pascals. Pascals is a pressure measurement. 50 pascals is about, it's like a 20 mile per hour wind, maybe 25 kph wind on the side of a building. So it's not a huge pressure. Permeability is another metric, which is cubic meters of leakage per hour for every square meter of envelope, and that's common for commercial buildings. So blower door testing, really, the concept is pretty simple, and that's why it's widely used, which is you use a fan to pressurize or depressurize the building, and you pressurize it to different levels. So this chart here shows 3 to 40 pascals. Normally, almost all the test standards say you need to test the building up to 50 pascals. So you take a bunch of pressure measurements, and then you take a bunch of flow measurements through the fan, and you get a relationship between flow and pressure. And all this does, for all of those standards mentioned, they all do the same thing, which is to derive this equation, which is Q is the amount of leakage equals C, which is the leakage coefficient, times delta P, that's the pressure difference to the nth power, and N is a flow exponent, and that's just related to the geometry of the holes. So all the major standards use that same methodology to arrive at that equation, and once you have that, you can report the leakage at 75 pascals, 25 pascals, 50 pascals, and convert between the different standards. So just briefly what a blower door test involves. You basically have to close the building up, and for constant ventilation systems like these fans, roof fans you have on the top picture here, you close them up so that they're not leaking air, and then most of the other things in the building you just leave as is. Like you leave the doors and windows locked as is, but you don't try to improve the air tightness of any of that. So no artificial prepping of the building air tightness. And then you set up the fans and the computers to run the equipment, although you can do it without computers. And for large buildings, this could take quite a long time to prep the building, going around taping things, and then actually doing the test. If everything goes well and you pass the test will be over in 10 minutes. It's pretty quick. All the labor is involved in setting up the test. So Green Star credits, you get 1 point simply for doing a test, and then another point for achieving best practice. These air permeability targets are from ATMA in the UK. So I won't belabor this anymore either. Permeability of non-residential buildings, a lot of this data Chris showed. These are, so yeah, you can see on the bottom right the range of green stars below 5 cubic meters per hour per square meter, down to 1, depending on the building type. So before you start panicking that this is impossible, let's talk about how you get an airtight building. So the first step is really to look at testing as part of envelope commissioning, and that means it's part of the quality control process. It's basically the thing you do at the end to pat yourself on the back to say, wow, look at what a great job we did along the way. So, and here's going through that. First of all, this is pre-design phase where you incorporate this into your regular commissioning plan. And then during the design phase, you choose materials and methods that are going to help you make an airtight building. So air barrier assemblies are tested, for example, by ASTM E2357 to leak at a certain rate. And that air barrier assembly includes an air barrier material plus all the things, the bits and pieces that go to put it together. So it's not just the product, but it's the product with a compatible sealant and the compatible primer, things like that, that all need to go together to make an effective air barrier. It's not just one material. So in design phase, you also should, once you have schematic designs, you should go through and define which zones in the building are going to be your conditioned zones and which ones are going to be unconditioned zones. This picture on the bottom left is actually astoundingly from a building where when we were testing it, they hadn't decided whether some of the zones were going to be unconditioned or conditioned. And so they were incredibly leaky, these zones, and they basically ended up saying, yeah, well, we're going to put that outside the thermal envelope, which it's a very bad time to be deciding that right when the building's supposed to be finished. So this is simple stuff that someone with an experienced eye can look through your plans and say, how are you going to put this thing together? Are the materials that you're going to use compatible? If you have this nice expensive vapor barrier membrane that you're going to use for the roof, how does that actually connect to the assembly at the top of the wall? How does that junction happen? Not sure if in Australia people read this book when they're little kids, but this is my favorite book when I was a kid. There's a song in this book that goes like this: the foot bone's connected to the leg bone, and so on. And so you go through the whole skeleton, sing this song as you're tracing your finger around the plans, and your finger should never leave the plans, and you say, the roof air barrier assembly is connected to the wall air barrier assembly, and so on, you know? So that's really the idea. You want to make sure this is a continuous line, and anytime you go over a complicated part, you say, how is the tradie going to actually do that? When you have an I-beam penetrating your vapor barrier, how do you seal around that? What joints, what tapes, sealants do you use to handle that complication? This is all about getting what you paid for. This building used very nice, very airtight, expensive, relatively speaking, Kingspan panels. Great product, but they didn't look at the plans to say, geez, it looks like we actually haven't completed the air barrier in this drawing here. So on the right, this is what's actually happening. They've got a nice insulated roof panel and a nice insulated wall panel, but then you could crawl down this hole. It's so big in this parapet. So this building, if I were an energy auditor, one of the things I'd do when I'm walking up around this building is I'd look at this with an infrared camera, and I guarantee you in the winter, this thing is going to light up because there's going to be a lot of air leakage coming out of the wall cavity and out through the top of this parapet. And that could have been avoided by some plan review earlier in construction. So you spend a lot of money on those metal panels and then they just don't do the trick in the end. So how are you going to do this when you're actually building the building? So the picture on the left is a mock-up that they did at this building where they've used the appropriate primer, and they used the appropriate, they used a really nice self-sealing, self-adhered membrane product, and then they had to switch caulks they were using because the caulk they originally had was not compatible with this very expensive membrane, and so they had to ship the correct caulk that was compatible with this over from America. So you have to try this out. It's a good thing to do a mock-up early on as part of your quality control to say, is what we're going to do correct? Do this even before you start building the building, if it's something new. Or visit a site that's is doing this. Lean on your reps, product reps, to give you advice about how to do it. You can't just get one product and hope it's going to solve all your problems. So building commissioning, building enclosure commissioning specifically, this guide here from the National Institute of Building Sciences is available free. It's chock full of information. It's like 300 pages, and it has specs that you can use for inspiration. It has guidelines, advice on contracts. It's really the mother of all commissioning guidelines, and it's available free from this website above. So at the end of the building, now you're going to test it. How much is it going to cost? These are not, these actually are pretty close to real costs for buildings that have gone through air tightness testing. Simple municipal building, 2-story building, you only need maybe 2 or 3 fans to do it. This building might cost you about $5,000 to test. A 6-story office building, maybe $12,000. Maybe you need 4 or 5 fans or something. Bigger buildings, depending on how you test it, it might take a few days to do it. So maybe you're looking at $20,000 for that whole building test. And then for a very large building, the cost is pretty dependent on the building itself. So the things that affect the price are where it is. I know that Melbourne's very well serviced with air tightness testing firms, and Sydney, there's not a lot of testing work yet in Sydney, but there are companies that are members of our organization that service Sydney as well. And another thing you want to consider is what experience do these people have who are going to be testing your building. Some buildings really you don't need the most expensive consultant to do it, but you have to be confident that they know what they're doing. And some of the things you might discuss with your testing contractors: who's going to do this preparation? Who's going to go around, make sure all the windows are closed? Who's going to tape off the HVAC on the roof? If it's a very tight building, if you've done well, then you're probably not going to need that many fans, that much equipment, and so there's less coordination, less preparation needed, so maybe the price is a little lower. If it's a very leaky building, you're going to need more fans to accomplish the same depressurization. Also think about what happens if you shoot for the air tightness and you miss it. So consider what you do in case of a failure. Just for example, a permeability target, varying permeability targets, tighter buildings need fewer fans to accomplish the same depressurization. But on the left here we have 10 cubic meters per hour per square meter, would need 56,000 cubic meters per hour fan capacity to meet that air tightness threshold. So that's about maybe 6 fans worth of fan power. So what a typical big building test would look like: you have fan setups around the building, and then you try to depressurize the entire thing at once. All right, I got to go a little faster. This is a picture of the large amount of equipment that's required for testing a big building. Most of the buildings that are being built in Australia can pretty handily be tested by a single firm with all of their equipment. But if you're testing a very, very large building, both the main standards referred to in Australia, AS 9972 and ATMA TSL2, say that you can test a sample of smaller parts of the building. And the idea is that you want to look at these various assemblies and characterize the leakage from each assembly type and the joints between them. So, for example, if you do a test on the top floor, you take the leakage from that building or that level, and then do a sample of the middle floors and then the bottom floor, and you get an aggregate for all of them. So A single compartment test is where you test one zone at a time, but a pressure neutralized test or a guarded blower door test is where you pressurize that zone plus the ones above and below it. The pressure between those becomes equal, and so there's no leakage between them. So you cancel out leakage between zones. This is more advanced technique. So how are you going to do this for a very big building? It might go something like this. If this is your hypothetical building, you test the top floor like that, and then you test a sample of the middle floors, and then you test the bottom floor. This is what you would do if you didn't have enough equipment to do the whole thing at once. Definitely, I would recommend trying to aim for doing the whole building in one shot, because I believe the results are more reliable, and putting together all these permeabilities of these different floors, hopefully they should add up to the same number that you'd get if you tested them all at once, but sometimes they don't, and that there is the rub. So that is actually all I have for my slides.
Excellent. Thanks very much, Sean. Thanks very much, Chris. Very, very interesting stuff. I have a couple of slides just to make sure people know how they can apply the Innovation Challenge to their Green Star project. So if some of you there have a registered Green Star project, be it legacy or new generation, you can go on our website. There's a screenshot of our website there. Go to the Innovation category tab. There's a little arrow there pointing to the Innovation Challenge credit. It looks like that. So it's a pseudo credit because it's an innovation challenge in the sense that we're still building up to a credit. So project teams can pick it up. They can use a CIR to work with the GBCA to implement that credit to their project. You'll be using a submission template, so there will be very little additional documentation. You'll outline how you've tackled it. You'll outline the standard that you've used, and you outline your result. Okay. Now we have a couple of minutes for questions. Let me just double check here. I believe we have had some questions coming through, which is great. So let's see. So we have a question here coming in from Simon. So there's a question, a Green Star question. Is the NETHERS pathway for residential buildings, is it a requirement that all apartments are tested individually? For example, testing 107 apartments one by one is a costly exercise. Is it acceptable to test a percentage of apartments or the whole building from a single entry, leaving all apartment doors open? I'll let Sean tackle that, but it's essentially whatever the standard says. That's the simplest way of answering that. Let's hear what Sean has to say regarding his experience.
Hello. I don't think that NETHERS actually has any requirements for doing actual blower door testing, but I would say that probably, so in New York State code, we actually recommended a different sampling method for multi-residential buildings where you can actually test just the apartment itself. And that's actually what we would recommend for multifamily buildings here in Australia, to do a sample of the apartments rather than the entire building. And there's methodologies laid out for that. Good source is ResNet in the US. They have information on stuff like that.
Thanks. I'll just say also on that I think it's the ATMA L1 for domestic that's called up in that residential part of the air tightness credit in Green Star. And so there'll be a section in there about that representative sampling method that will have a detailed answer to that question. But I think that the big picture answer is no, you don't have to test all 170 of them. You can pick a representative sample of orientations and construction types and follow the standard to get a compliant result.
Excellent. Thanks very much. We'll have a few more questions. Let's see how many questions we can tackle this afternoon. Arvind asks, what are some proactive steps a contractor can take to design an airtight building? Well, I think some of that comes from the actual design of a building. So ideally, there would be some design requirements within that. But let's have Sean and Chris add their 2 cents to this answer.
Well, I would echo that comment that a lot of it comes from the project design to begin with. I think if it's a residential building, it's a lot different than if it's a commercial building. The builder might have a lot more latitude to do to try to define an approach for air tightness. A lot of good resources are out there from Passive House, from Energy Star in the U.S., Building Science Corporation. They have really excellent free resources that are available for people doing residential construction specifically. And then for commercial construction, I would look at that National Institute of Building Sciences Building Envelope Commissioning document that I referred you to. It's pretty big, but it's got everything that there is.
Just saw there's another question about for the facade area in meters squared, is this just the walls? What about the ceiling or elevated floors? So it's the whole building envelope. So the number is meters cubed of air going out per meter squared of external building envelope at that 50 pascals of pressure. So yes, all of the surfaces of the building are included. And I think there's a related question here about the good practice or best practice international standard around 2 meters cubed per meter squared per hour, and is that a recommended absolute minimum? So I think yes is the answer there. You're really asking a question about climate zones. So your point references the slide I had around the UK and Italy have set 10 meters cubed as the minimum standard, whereas Sweden and Norway have set 2, 2.5, and Germany's 4. So your question around is 2 really appropriate for everywhere? Well, a good as in an excellent ceiling around below 2, yes, that's the same rule everywhere because that's an absolute thing. But for the minimum standards, yeah, perhaps you would vary it. You might decide that 10 or 15 is appropriate in Australia because we have a milder climate. So yeah, for a minimum standards approach, you would probably vary it, but for the best practice end, you would probably stick with those international best practices as absolute, because Passive House, for instance, is applicable in all climate zones around the world, and it sets a performance criteria around 1. So yeah, I think that at the best practice end, we should be aiming for those low absolute numbers.
Excellent. Thanks, Chris. There are lots and lots of questions about cost. I think we'll skip those because Sean had some indicative figures of cost in his slides. There are a couple of other questions we'll try to tackle here. For example, there's a question about points of failure. You know, where are the main points of failure? Would either one of you like to touch on that?
Sure. Usually, if you have a building that's built with fairly airtight materials, like whatever your sheathing material is or your windows, the problem isn't the materials you use necessarily, it's how they go together. If I could just pick one point where I think is the biggest weakness, it would be the roof wall junction in most low-rise buildings. This part, especially with the way the roofs are built here in Australia, you end up with some complicated joints at the roof wall assembly that really need attention, and that's usually, luckily that's actually one place where it's pretty easy to fix, but that's often a very weak point.
And it's the same in commercial buildings around the joins. You wouldn't typically expect a great deal of leakage through an engineered curtain wall facade, which has been factory designed to clamp together in a pretty effective way, but where that engineered facade meets a concrete element either vertically or at the roof or at a plant room, for instance, where there's an unconditioned space mid-rise and maybe there's ground mid-rise and top level plant rooms, those junctions there are probably going to be weak points that you might want to investigate.
Excellent. Thanks very much. We'll take one more question, and then we'll try to answer the other questions that are coming through on our website. The last question I wanted to try and tackle relates to in situ testing. So the question goes, to isolate centralized ventilation from testing, how effective are the in-situ control hardware, example VAVs and shut-off dampers. Did you want to try and answer that?
Yeah, I wouldn't trust those. So basically, I would never trust that a damper is fully geared to close in the correct position. And furthermore, most of those aren't made to be hermetic anyway, and that's what we need is hermetic seal. So what I would do is go to the roof where the system supplying the VAV boxes is, go to that air intake, seal that off there. That's the kind of stuff you have to do, is go around, basically find the entry point for that air leakage and seal it there.
So there's another question about contractors who can carry out this kind of work. Yeah, there are some contractors. Mike Rogers from Air Barrier Technologies provided me with a lot of the data that I used in my presentation, so I think it's fair that he gets a plug for being open and transparent and sharing some of his test data. He's certainly someone that you can get in touch with. He has blower doors and is an experienced air testing person. And if not, the work that Craig McLaughlin's doing at the Sustainable Buildings Research Centre down at University of Wollongong, or Sean, obviously our speaker today, all of those are great contact points for finding out who can do this for you.
Excellent. Thanks very much, everyone. Thank you very much, Chris, for attending and sharing your knowledge with us today. Thank you, Sean, for coming along and chatting to everyone who's online. I think that concludes today's webinar. Just one last reminder and plug there for Green Cities, our national conference that's coming up from the 22nd to the 24th of March. Be there or be square. It's going to be cool, and there's lots of good speakers again this year. So I hope to see you all there, and check out our website for the recording for this session, as well as the answers to the questions that have been coming through. Thanks very much for attending, and have a lovely day.